In this tutorial I'm going to describe setting up and running Castep. In the Oscail help you can look at the tutorials, and we're going to look at a tutorial in the crystallography section on Castep. Now the first thing you need to do when you're setting up Castep to run on a PC with Windows 10 is to download Ubuntu from the Microsoft Store. This is free, and the instructions for it are on the web for installing it. It's easy and straightforward to do. The second thing you need is a Castep license. Now, when you get a Castep license, you will be able to download the tar file, which contains all the Castep files. Create a folder on your C drive, C:\Castep, and put the tar file in that folder. Now start Ubuntu by clicking on the toolbar button or taskbar button, and the command you type into the Ubuntu window is cd/mnt/c/Castep. That will change to the Castep folder, and in that folder where the tar file is, type the tar command. This will unzip the Castep file. When the file is unzipped, you can look at the readme install file in the Castep folder, and you'll see instructions on how to install the package. Now the package I used was 2011, and this was the command required. There was an error in the instructions. There was an extra S in build essentials. This installs the various operations and programs needed by Castep. You also need to install MPI, and this is the command for installing MPI. Now the next thing is to change to the Castep directory using CD space CAS in capitals, press tab and it should find it, and when you're in that folder, change to super user with sudo su, and you now type two commands, make and make install. Both of these will generate a lot of screen output, and you need to wait for make to finish before you run make install, of course. When you have these two run, you need to also install MPI. This should give you the commands castep.serial and castep.mpi. Now, if you have an OBJ subfolder of the main Castep folder, then it should look like this, and if it does, then everything should work out fine. Now the next thing we want to do is install Nano. It's very useful for editing Ubuntu files. We also need to download the K-point grid generator from Mueller's lab, and when you've that downloaded, you should also check where you've downloaded and download it to the correct folder. Put it in mnt/c/Castep, and then type these commands for the programs that the K-point grid generator needs. Now when you have that done, edit the profile to put the path to the serial and parallel versions of Castep and the grid point generator into the profile so that the path to them is known. And you don't put in the initial hash, of course, when you're putting those into the profile file. Now when you've that done, everything is ready, and we just need to generate input files for Castep. Now cell and param files are required, but also POSCAR and prelim files. These will be automatically written by Oscail. These are VASP input files used by the K-points grid generator. We're not going to use VASP, of course, we're going to use Castep, but we'll see that in a minute. Now, to generate the input files for a filled cell, in this case I use the HPS1 job, which is in the Ortex folder. Open that file in Oscail and do a default lattice pack. Make sure you check the Castep files checkbox on the lattice pack dialog and click OK. This will generate the files you need. You also need to create a folder into which you want to put these files, and I use a subfolder called examples and then the various jobs we want to run, each one in their own file, in this case HPS1. And so we will have 6 files because we have the cell and param files in 2 varieties, for medium and fine precision. So 4 files of cell and param type and Oscail and precalc. To generate the input files for gas phase simulation of an isolated molecule, we put it into a 20 angstrom box, which is the default, and it works for most cases, but you can vary the size of the box. And uniquely here we also allow you to generate an orthorhombic cell. It doesn't have to be cubic, because a time advantage can be gained by fitting the molecule aligned into the cell. And if you can reduce the cell volume, the calculation will go faster. For example, if you had a flat molecule which is only 1 atom thick in one direction, then you could reduce the unit cell dimension normal to that direction, normal to the flat molecule, down to about 12 angstroms. You need to be careful doing this. But in this run we're going to use defaults, the 20 angstrom cube box. I'm not going to go through the details of doing an aligned molecule. Now if you click OK, we will generate the input files for the isolated molecule. Now to run Castep, you open the Ubuntu window again, if you haven't it already open, and go to the folder where the files are, and then type get kpoints. Notice the KP in the center are in capitals. This will generate a file called kpoints, and this file is written in VASP format. We are just going to take the fractional coordinates for the kpoints out of it. So copy those files out, those lines out of it, just the fractional kpoints. Now notice they have 8 written after each of the XYZs. These are the probabilities. Now in Castep the probabilities must add to 1. Here they add to 32. If you divide each of them by the sum 32, you get 0.25, and then the 0.25s, the 4 of them will add to 1. So divide each of the kpoints by the total, and then you'll get the correct one for Castep. Now when Castep is running, we have a program ucastep space job name, which is a DOS program, so you type it into the DOS box, and this will generate a synopsis of what is going on. It's very useful so that you can monitor how well the job is doing. In this case the job is actually finished, because you can see after iteration 72 it had a completely satisfactory situation and the thing was finished. Now let's look at a run. We're going to do a run on TCY QME CC. All you need to do the run is a shellx INS file. This is the INS file for this job. You need the space group symmetry operations and the atom coordinates. Now to run it, all you need to do is go into Ortex and do a default lattice pack as we saw in the tutorial, and make sure you check the Castep files and then click OK and exit Ortex. The files are now written. So we can look at the files and we see POSCAR and precalc and 2 param files, the medium and fine basis precision param files, and then a medium and fine precision cell files. So these 6 files are required. So we'll copy those, and in this case we're going to copy them to a USB stick because we're going to transfer it to another computer. So there are the 6 files for the filled unit cell run on Castep. Now we also need the gas phase simulation, and that's very easily done by using run job formats, and the very first option is the one you need. SM is single molecule Castep. Click OK, and immediately the dialog comes up. If we say OK, that we get the 20 angstrom cube. Now we can look at the files generated for that. And you can see the first 3 characters of the job name are used, and then the integer versions of the unit cell dimensions are used to characterize the thing. And there's also an INS file written. This can help you scan the lattice for contacts if you wish. Now we're going to put these in a subfolder called SM for single molecule to keep the single molecule and the filled unit cell apart. So now we have all the files we need to do a Castep run. Now switching to the other computer, we open the Castep main folder, then examples, and now generate a new folder for the job we're going to run, which is TCYQMECC. TCYQME is what I call the folder, and we're going to put the files in there in which you're going to use to run the Castep job. So on the USB stick we have the files we generated, copy all of them, and paste them into the folder we just created. Now we should be able to run Castep. So we press the Ubuntu button, we get a Ubuntu window, and we cd space /mnt/c/ca and tab, and you should see Castep. And you can do the same cd space uppercase CAS tab, and then cd capital E lowercase x examples, and finally to the folder we just generated, TCYQME. And if we type ls, we see the files are listed in Ubuntu there, and they're the files we have over on the left. So all is well. Now we can start Castep running, but we need to get the K points first of all. So get KPOINTS with the K and P in capitals, and this, as we can see on the left, has generated a K points file. Now we edit that file with Notepad, and we copy out the fractional positions of the grid points, the K points. So we copy that and we paste it into the cell file we're going to use. This time we're using the fine basis precision file, and we put them into the K points block there. Now we need to change the probability into Castep form. There are 4 4s there which add to 16, and 4 divided by 16 is 0.25, so change each of them to 0.25 so that the probabilities add to 1. And now save this file. Now to run the file, we need to watch the program running, so we'll put on the view of the CPU activity. Now we type castep.mpi space job name tcyqmecc_f for the fine basis precision, and hit return, and you can see there's an immediate response of the CPU activity, but it takes about 2 minutes before the system gets going. You can see the first thing it's done is generated 3 files there at the bottom. They're the pseudopotential files, but it takes it about 2 minutes to get the optimization underway. You can see now the CPU is going up, and the fan and the computer starts to make more noise as the thing goes up close to 5 gigahertz. The speed. So it's running fairly efficiently. It's using 80%, 90% CPU. Now, if you click in the window up there and type CMD, you get a DOSBox open in the current folder. This is a very convenient way to open a DOSBox. Now we're going to use this DOSBox to run the uCastep program when the system has been running for a while. Now it's been running for a while. We type uCastep space job name TCY QME and press tab, and it went too far. We just cut it back to the job name, and this has generated pptest.cao, and if we edit that file we will get a synopsis of what's going on. We can see the last fractional coordinates means it hasn't optimized, but it has 15 iterations done, and it's begun to reach convergence because one of the criteria has been satisfied in the last few cycles. So we need to wait more time and do it again, and this time we see we now have refined fractional coordinates, so it's now finished and the 3 criteria are satisfied, and we now have the final energy. The last cycle only changed 0.04 of a kilojoule, and so we have the energy of a filled unit cell. That's the energy there in kilojoules. Now we want to do the gas phase simulation run, and for this we go to the SM folder, and these are the files we need, and they're already there, and we need to switch Ubuntu to that folder, so cd sm, and now we can run Castep on these files. So you can see the name there, TCY, and press tab and see what you get, and it got 2020, but you need an F at the end of it, and it's now running. And the first thing again is the pseudopotential files are generated, and you can see the CPU goes, and after some time we can change this to SM as well, and uCastep and the same job name TCY 20, and cut that back, put in F, return, and we get a new pptest.cao file. We can edit that to see how the job is going, and we can see again it's not finished. It has only run 4 iteration cycles and it's changing 8 kilojoules per cycle, so we need to wait longer. And now, after some more time, we look at the pptest.cao again, and we see that it's now refined, and we've got the final energy of 1 molecule in a 20 angstrom cubic box. Now we can calculate the lattice energy. To do this, we need to go back and bring up the energy of the full molecule, or the full filled unit cell again, and here it is at the bottom. Now we need to copy these into a spreadsheet, but it's a good idea to copy other information as well. Now the information we should put into the spreadsheet should include the job name. To avoid confusion, put the job name into the spreadsheet, which is up here at the top. Just copy the job name and paste that into the spreadsheet. Now we should also take the cutoff voltage, because that determines the basis precision, and for a fine precision run it's 843 electron volts. We should copy that as well. Now our energy for the filled unit cell, we copy that in kilojoules and paste that into the spreadsheet. And we label it with kilojoules because we want to make clear it's not in hartrees. So the next thing we need then is to get the energy. Oh, sorry, one last thing is it's as well to put the DFT functionally used into the file and make sure that PBE for solids, which is the best one for these type of calculations, is used. It's as well to record that because you'll be putting it in a publication anyway. Now this is the energy of a single molecule. We copy that energy and paste that into the spreadsheet in a section which we will call SM for single molecule. And so paste in the energy of the single molecule. And now the lattice energy is the energy of a filled unit cell divided by Z minus the energy of 1 molecule. So that's equals B6/4 minus B9. And we see there's the lattice energy, minus 137 kilojoules.